Hi and welcome to Unit 2, Topic 3, Video 16. And in this video we're going to continue our geometric transformations. We're going to look at dilations and then we're going to look at shears. So dilations is not too bad. A dilation is where we grow or maybe decrease the value away or towards the x and y axes. So in this case I'm saying, what if I want to move away from the y axis? Okay, and in the example I've got, what if I want to double my distance from the y-axis? So I'm taking this coordinate and I'm translating along the x-axis. Sorry, not translating, dilating along the x-axis. Now you've seen this in your function work. We do this kind of stuff. We do an x dilation or a y dilation. You've seen where that exists. In terms of matrices though, if I want to move away from the y-axis, I have to increase my x value or decrease it if I'm moving towards. So x is going to go to 2x, and y just stays as y, so it stays in the same y value. And that means that my dilation will be 2, 0, 0, 1. That keeps it the same. Now generally, this will look like A, 0, 0, 1. This will be my general transformation and we'll shift it A away from the y-axis. What if I want to move away from the x-axis? So let's say I want to increase the height of something by a factor of 4. So x goes to x and y goes to 4y. I get the same result, but the different way around. 1, 0, 0, 4. You have to excuse that, it's my washing machine. 1, 0, 0, 4 will give me that transformation. So this is good. Now the generalized one here is 1, 0, 0, b, and that will be our general transformation to shift it or to dilate it a factor of b. And away from both the x and y axes, and there is an example here, takes us A, 0, 0, b. And this is on your formula sheet. So you just need to recognise it. You don't have to memorise that, but it just that will move it away from the y axis by a factor of a and the x axis by a factor of b. A horizontal stretch, factor of a vertical stretch, factor of b. So example 2. Determine the transformational matrix that would take each vertex in the unit square and dilate it to be a 5 by 3 rectangle with bottom left vertex at the origin. So I'll just quickly describe this unit square. It's worth looking at this visually. See old, if it's tricky, draw a picky mantra, which I quite like. Here's my unit square. And here's my 5 by 3 rectangle. So 5 usually denotes the x value first and then the y value. So I'm just going to label this. This green is the origin, it stays the same. This point shifts up to here. This point shifts out to here. And this point shifts out to there. Okay, now it's important to put down here a recognition that we've gone out to 5, 3 from 1, 1. We can do all the work there. What's our general transformation that will make this happen? So our unit square, of course, is still 0, 0, 1, 0, 0, 1, 1, 1, or some variation of that. And our transformation, I hope you can see here, will have a 5, 0, 0, 3. And if we do this multiplication, we end up at 0, 0. So bottom left corner is still on the origin. And then we get to 5, 0. And then 0, 3, and then 5, 3. So that is green, orange, light blue, purple. And that's our transformation. And it matches exactly what we said here. So aren't we happy? That's example 2. Pretty easy. Okay, let's talk about shears. Shears are an interesting one. This is where we get a chance to mix up our x and y a little bit more. So shear is a translation of points based on their distance from the x or y axis. So I've got a couple of examples here. It might not look like it, but I've got A and I've got B, but operating under the same shear. So the shear is taking, we'll start with B. The shear is taking B and it is moving every point along the x-axis based on how far it is away from the y-axis. So see how these 2 points here didn't move? I shouldn't use light blue, I would have used it. Let's use purple. Those 2 points didn't move because there is 0 distance from the y-axis. These 2 points here are distance 1 from the y-axis, so they've moved along 1 from where they were. And that's all good and well A, on the other hand, up here, these 2 points are 3 away from the y-axis. Sorry, they're 2 away from the y-axis, so they've moved 2 from where they originally were. And these 2 points are 3 away from the y-axis, so they've moved 3 from where they originally were. So we're basically taking whatever the y value was and adding it to the x value. That's what a shear does, and it has the effect of slanting a shape. So a shear is like a shape slant. In this case, nothing special is happening to the y. Do you see how the shapes haven't moved up or down? All the coordinates individually have not moved position vertically. They've only moved horizontally. So we get this y goes to y, but we get x goes to x plus some number of y. And in this case, I've just moved it a single y. So these guys here, they moved one, that's still highlighter. These guys here, they moved 1 spot because they're 1 above the x-axis, 2 spots, 3 spots, just one value of y. So basically, x now goes to x plus y. And y goes to no x, but it remains as y. So a shear should remain with a 1, 1 here, and then we'll have some different values appearing here and here, depending on what the shear is achieving. And we get this transformation down here. Now, of course, this takes us to, if I expand this out, x plus y, and then y. And the generalized version of the shear is 1C01 for a shear parallel to the x-axis. And if I go down now to look at the parallel to the y-axis, in this case, I'm moving out. I've got A and B. So we've got x goes to x, y goes to y, plus dx, some number of x. Now, I haven't been very specific here in respect to these shears because I've started at some point out there, and I'm saying that this has moved up by a factor of A, and this has moved up by a factor of B, but I've not made that very clear. So that's B and that's A, which is again a 1-1 relation. But our generalized form of a shear in the y-axis is 10D1. And the larger D is, the more this shape gets pushed that way and slanted. Now the slant will remain the same because this distance is pretty consistent, but it'll move up and down. So that's shears. Now they're a bit tricky, but seriously, have a play around with them. You'll find that they're not too bad. In the diagram shown, determine the shear that took A to A dash. Well, I can tell you straight away, so we're looking for the transformation, that it's a shear parallel to the x-axis. So it's going to be 1, 0, 1, and it's this C value I'm trying to determine. Now, this is how we play with it. We've got a couple of ways of playing with it. The first way is, let's just take this major point. This, the outside point. Any point will probably do, but that outside point is usually the best. And just go, well, we know it's 1C, 0, 1, and that's multiplied by the original point, 2, 2, and it's taken to the new point, 6, 2. And so I can do this calculation now. 1C to 1 gives me 2 plus 2C, and 2 is equal to 6, 2. And then I can just go, well, that means that 2 plus 2C equals 6, and C is equal to 2. That's one way of doing it. The other way is a little bit more logic, which is probably not the best way to go about it. But I can see that this point here is 2 above the y-axis, and it's moved out to 6. So it's moved 4, and it was 2, so that means that I've got a movement of 2 times that height. And that means that C will be 2 as well, another option. So T is equal to 1, 2, 0, 1. I've probably found that in terms of understanding, this one's one that students do find a bit challenging, but I have found in the past a lot of success with students watching me go through this, going back and having a look at the examples in their textbook, reading through it in a bit more detail, then come back and watch the video again. Honestly, that 3-part process often clears things up, and then take some time to do some questions, write down every question that you have, every unknown you have, and take them straight to your teacher. Easy peasy. All the best.